Move this over. Good. Students online, are you able to see the board? Shubham,
Yes,
Shreya?
ma'am.
Okay. How clear is my voice?
Ma'am, it's clear.
Okay. So for the next 15-20 minutes, you will have to see the class like this because we had some technical issue here. Okay. The projector will be here in about 10 minutes.
Okay, ma'am.
Okay. Yeah. Is this better or is this better?
This is better.
This is better or this is better?
So the previous one.
This one is better?
Yeah.
Okay. So the frame is okay, right?
Yes, ma'am.
Clear? You're able to see what ma'am, right?
Yes, ma'am.
Okay. So if you have any issues, just drop a message in the chat box. Okay, somebody will reach out to you.
Okay, ma'am.
Hello. Hello. What happened? So, what is the X-rays impact? Huh? I will solve. No worries. So, what the thing which I have taught yesterday. Comfortable. Yes. So far, I have taught. What are the things we have seen in yesterday's class? Be a little bit louder. Packing density. Packing efficiency. Three-dimensional. What happens in three-dimensional hexagonal closed packing?
Third layer is being placed in the
First, you are placing the second layer on the top of it. What are you observing?
triangle.
Tetrahedral trigonal. See, half it is coming for me. No. Then, after placing the third layer, after placing the third layer of that while coming up. No, after placing the second layer, you are observing two types of voids, tetrahedral and octahedral. After placing the third layer, now I have been said about the HCP and CCP. And I have calculated the coordination number. The CCP is nothing which is equal to FCC. I have drawn a picture. Right. After that, what happened?
Calculate the
Atomic radius, edge length, packing efficiency, percentage packing efficiency. Yes or no? Location of tetrahedral and octahedral void. Yes, what is the location of tetrahedral void for FCC? Like calculate it and say the numbers.
8.
For tetrahedral void, it's 2n.
2 8.
What? 8 for FCC. Okay, fine. For BCC,
4. 4.
I'm not asking n. It's 2n means what is the value?
2 8 4 greater than 2.
So I'm asking for BCC. So 2 into n.
4.
4. Okay, fine. So what is for octahedral? It's simply n. Okay. After that, we got into atomic radius, edge length, and percentage packing efficiency. Why don't we attend the physical class yesterday, Vaishnavi? Okay. Okay. So what is the atomic radius? What is R value for FCC? A by 2. You are clear with that? For FCC?
A by 2.
A by 2. For BCC?
Root 3 by 4.
3. A by 4.
3 by 4.
Don't get mixed up. What is the percentage packing efficiency for SCC? The remaining will be void. So, okay, likewise, I said it for BCC and FCC. FCC will be more efficient. That is similar for HCP and CCP. Clear? After that, what we have discussed? Density. I think before that, for packing efficiency, I have given a formula. What is the formula? Percentage packing efficiency is equal to volume of the particle divided by total volume of the units and into 100. Is that the way to represent volume of a volume of the particle is nothing but 4 by 3 pi r cube divided by a cube, right? Then finally we came to density. What is the formula of density? Into mass of the atom. That I have said you have to take it in terms of moles. Yes or no? Yes. Molecular mass divided by so with this formula only you have calculated the problems. Yes, I'm coming to that part. Which problem you want to answer? Sodium. Yes. Doing that only. Very. So what are the given informations? So sodium, right? BCC structure. They are given as a BCC structure. Distance from its closest neighbor is 369. So this distance from the closest neighbor means it is diameter. So diameter is 365.9 picometer. Right. And what they have been asked to calculate, find the density. So this is the density. So for this, what we need initially, we need the A. Right. So here they have been given density. So first, density is equal to 2R. Yes or no? Density is equal to diameter is equal to 2R. Diameter is equal to 2R. So diameter is equal to 2 into R. So here we can substitute diameter is equal to 365.9 picometer. Have you done this? Sorry. 365.9. So what happens here? We want to find the radius. So R is equal to 365.9 divided by 2. Clear? So what is your value? What's the value? See.
Can we round it up?
We can round it off as 366 divided by 2, which is 180. So this is your radius. Now we need to calculate A, right? So for BCC, what is the A value? So BCC is equal to R is equal to 2A by 2. Now we want to determine A, correct? So A is equal to 4R divided by 2. Clear up this thing. A is equal to 4 into what is the R value? 183 divided by root 3 values 1.73. We can take it as 1.7 to make the calculation easy. Yes or no? 1.732 means this 3 is not more than 5. So we can round it off this value. Yes. So what will be the answer? Do it. How to do it? 4 into 183, which is 732 divided by 1.7. So 732 divided by 1.7 is
430
430.5. Clear? Till this step you got the answer. Yes. Now substitute here. See, your answer is your options is given in terms of meter cube. Correct? This is in picometer. So no.
Yes, ma'am.
So convert it into meter.
Yes or minus?
Minus 12. So 430.5 into 10 to the power minus 12. Clear? So now substitute here. Shall I do it? What is your setup for BCC? Molecular weight for sodium
23.
23 exactly. Divided by this A cube is 430.5 into 10 to the power minus 12 the whole cube into 6 into 10 to the power 20 times 0.06. Now put this into 23, that is nothing but 46 divided by 430.5. See, to make this as a round value, just bring this decimal here. Yes or no? So 4.3 into 10 to the power plus 2 or minus 2. Plus 2 or minus 2. Plus 2. Right to left. Plus 2 into 10 to the power minus 1. So which means we can write it as 10 to the power minus 10. Clear? The whole cube into 6 into 10 to the power 23. Yes or no? Till now you got this point. Now 46 divided by 4.3 into 4.3 into 4.3. What? 4.3 into 4.3. That's 1, 16, 17. So 2, 9, 4. This is the value. What? 4 point.
It should be 2.
It should be 2. So 4.3 into 4.3. It's 18.4, right? Into 4.3. 79.50 means we can take it as 5. Okay. Into 10 to the power minus 30. Yes or no? Into 6 into 10 to the power 23. Correct me if I'm wrong. Yes. Now multiply with 79.5 and 6. Yeah. What? Now we can cancel. It's 23 and 3. Now 23 divided by 79.5. 79.5 into 3, which is 238.5 into 10 to the power. What is this thing? Minus 7. Wait. Okay, fine. Yes. Good. Minus 7. Yes. So now what happens? Just divide this 23 divided by 38. 1 by 10. Is 0.096. That is like we are taking Clear? Huh? Clear with this thing? Yes. Like, what's the difficulty you face in this problem? Huh? Calculation. Already I have disclosed that thing. Okay, now do this sum. Xenon. What is the answer? What is the answer? What is the radius? Diameter? Right angle one. Okay, wait. Metallic gold. You want me to write or shall I dictate? Metallic gold is crystallized into cubic cell that is having, they have given cubic cell. Okay, which means CCP. That is nothing but FCC. Then I don't disclose the options here. Just for your purpose, I have disclosed the options in okay. I think here we have converted it to meter cube. Maybe in options, maybe it can be around centimeter cube also. Maybe this 10 to the power minus meter. Centimeter is 10 to the power minus. Okay. Yes. Metallic gold is crystallized into cubic cell. That is first information is FCC. That is having H length. That is A is 4.24 angstrom. Here, your first question is find the closest distance between gold atom diameter. So first one you have to calculate the diameter. So here what we have given H length. So what you have to do first? First you have to find very good R value. So R for FCC, R is equal to A by 2. Substitute the A value there. So your A value will, R value will be, you will be obtained. Then diameter is equal to 12. That's it. In angstrom itself, I don't convert it to meters. Have you done this calculation? Huh? One.
Diameter is 3
We calculate the last one. 3. Yes. So what is this one? This one's answer. Radius. 1.5. Now diameter is equal to 2R.
First of 2R, so we got 2.
Is 2 into 1.5 angstrom with 3.01. You can take this 3 angstrom. Yes, this is the first A question. B question. Find the coordination number. For CCP, yesterday, I have set the coordination number. Exactly. How many layers will be there? Types of layers. A, B, C. Right? Correct or not? Yes. Center particle. One like this. One like this. So, yes. I have taught this yesterday, right? Not last year. Okay. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The coordination number is 12. What is the percentage parting efficiency? 78. Yes. So finally, we have concluded the questions. Shall we move to the next topic? Here is still this. Any doubt? Shall we move to the next topic? Next one is actually, so far we are dealing with last things we have density, I think this. Now we are getting into the relationship between void and atom. Right? So we came to know there is voids from the three-dimensional force family, right? Octahedral and tetrahedral void. This void is present either inside the unit cell or maybe at the edges wherever. Okay, tetrahedral void. So for FCCE, okay, there is four, like in a simple unit cell, there will be four body diagonal. So in this four body diagonal, can I repeat the four body diagonal? So in the FCC connecting all the four body diagonal, we will be obtaining 8 tetrahedral voids. Yes. So likewise, we have to know the relationship between the atoms. Atom means the atoms can be present in the corner or faces or body center or edge or wherever it may be. Okay, the relationship between that atom and the void and the radius. Okay, so first one we can find the relationship between octahedral void and its atom. Okay. Why are you studying this thing? Why you are studying this one? Relationship between the void and the atom. See, definitely, whatever the pattern may be, whatever the atom may be, whatever the unit cell, definitely there will be a presence of voids. Okay, definitely there will be a connection between the atom and the void. Okay, that's why you are going to study, and there is a radius of the atom. There will be radius of the void is also present, right? Okay, if the atom is of this shape, okay, if it is spherical, another atom is spherical, a small spherical, okay, sphere will come and sits in the void. Yes, correct. This one, correct. So that can be, we are saying it is a tetrahedral void, octahedral void. Inside it. Yes. So now, first one is the relation between octahedral void. Okay, guys, listen carefully. If don't write this word. Yesterday, I actually observed when I'm teaching you to keep on writing, you will be having the confusions. Okay, I noticed in FCC, PCC, and FCC. Okay, so please listen. If this is a book, I don't rub it, and finally you can copy. I'll give the time. Okay. So first, octahedral void. In FCC, I said one octahedral void is present at the center. It's not more. This is FCC, right? So connecting all these points. Here, octahedral void. This is at the center, right? One edge is also the octahedral void will be 1 into 1 by 4. Totally we have said it's 4, but I'm saying only at the center because we need to derive the radius. Okay, if the radius of this octahedral void is of this much value, definitely all the octahedral void will be having similar value. Okay, so for the better understanding and for the imagination and for the visualization, I'm taking this. Okay, so since you have these points connects and in the center you can see the octahedral void. Correct? So on top, bottom, left, right, front, back. Correct? Here your octahedral void. Yes. Now we move top and bottom. Why in this sense? See, we are going to calculate the radius. definitely we want to visualize a triangle. Yes. So the top and bottom is not necessary for us in calculating the radius. Clear? So I'm just taking this 4 lattice points. Okay. Actually, your R will be 0.414 smaller. This is your value. Okay, this is your radius of your octahedral void, but I'm going to derive it. Okay. Now, see, this is left. This is right. This is back. This is right. So left, right, front, back, left. Now, make this particle as A, B, C. Now here will be your octahedral void. So now, all the 4 points at an octahedral void I have drawn this. Clear? Have the imagination. Now, I'm taking this. Okay. This triangle. Okay. A, B, C. Okay, apply the Pythagoras theorem, which means AC square is equal to AB square plus BC square. See, this A and B, that is nothing but a H left A. We are taking this thing R, this thing R. Okay, this is R and this is R. Look at me. Okay, yes. Now here, I won't repeat it again. And here, this is the H and A. Okay, so definitely here also the radius will be R. Here also the radius will be R. Clear? Now, here it is an octahedral void. Okay, there when you are calculating the atomic radius and H length, what we have represented, it's represented by smaller because they are all similar lattice points or particles or atoms or ions. But here, this is atom, a particle or lattice point, but this is void. This is a void. So definitely we need some differentiation, right? So this is R. This is also R. This part, it is capital R and capital R.
Which so the radius of the void is capital.
Drawing this one. Okay. Now, this is the thing I have drawn. This R, A. Say yes or no. R. See, actually, I need to connect these two things. Okay. But for the expansion of this void, I have drawn it in this way. R. This is also R. This is A. And here R. Here R. This is a void. So to make the differentiation, this is capital R and this is capital R because it is a void. H length. A square plus BC square. What is BC square? A square. So AC square is equal to, they will connect. Don't need to watch it. Okay. AC square is equal to 2A square. Clear? So now we can write this as AC is equal to 2A. Clear? This A can be represented as A is equal to R. So AC is equal to 2 into 2R. Clear with this thing? Now shall we move to the next one? Now, for AC, this is AC. Clear? 2 into smaller, 2 into capital. Yes or no? Yes. So AC is equal to 2R, that is small r, plus 2 capital R is equal to root 2 into 2R. Got this point? Now, take this one. 2R divided which is now 2 capital R plus 2 small r is equal to root 2 minus 1. This plus 1 goes here. Here, cancel this thing. So now capital R divided by small r is equal to 1.414 minus 1. So capital R divided by small r is equal to 0.414. So capital R is equal to 0.414 small r. This is the relationship between your octahedral void and atom. Clear? Any doubt? See, the top and the bottom is not necessary. Okay, because we need to visualize the triangle. Clear? Got the point? Now, in terms of tetrahedral void, what happens? In one FCC, there is 8 tetrahedral voids. Yes or no? This relation is very, very important. Okay? This will solve problems. Yeah. Whatever I'm teaching, that is up to your NCERT syllabus. I'm not going again. Okay. Everything will be asked. They will ask everything here. So don't. Definitely, you can't say that. That's why I'm just trying to.
Students are able to hear, those who are online are able to hear.
Yes, sir.
This is one part. Yes, I agree. Now, what is A, B, but the tetrahedral void will be the height. So first we put A, B, C. Now we have to calculate A, B. We have to calculate the void, right? For A, B, C, like 2x squared. This is what we want to do. Now we have to do it for A, x squared plus a squared. 2a. Now take a triangle AD. In AD only 2 atom and in mid the void will become. Wait, don't worry, I'll draw. Shall we move? Enough, Pandita. What are you doing? I asked you to solve. Seriously? Okay, then disclose what you have discussed so far. Now I'm doing for tetra. Discussion over. Now shall we get into the topic? Come. Yes. So I am not going to draw the entire FCC. I'm not going to draw the entire FCC in itself, and I'm not going to cut it. I'm going to take only the one part. Yesterday itself I've done it, right? See, now take it for the triangle. இது minimize பண்ணுமா? I've drawn the triangle. Calculate it for ABC triangle. When we will get a break time, when we can take this, that's your ultimate goal and aim. Now, first, ABC is a triangle. Now we have to take another triangle which comes from the void. That is ADC. Because if we AD only, you can see the diagonal line is intersecting. Okay, A, C, in between the word is there. Yes or no? Calculate. Okay. Now, see, your void will be present here. Tetrahedral void. Okay, clear. So now for ABC triangle, it will be AC square is equal to AB square plus BC square. A square, this is A, right? This is A, this is also A. So AC square is equal to 2A square. AC is equal to root of 2A. Clear? You got this thing? Now, this AC, okay, this is actually the lattice point, the atom or the particles or anything, right? So this AC can be represented by this point. Correct? Huh? So now,
This is R and this is, so this AC is nothing but 2R. Now you got my point. Why I have done this? Why I have derived 2R? You're getting my point or not? How is the? See, this FCC, what happened? There will be two atoms like this. And another two atoms, all the 8 corners, it will be there. In faces also, there will be like. So every atom will be close. Correct? So we are calculating, if we are taking the radius, AC means definitely the radius of A and the radius of C. So 2R. Don't think I have connected A and C there. It's not like the radius. So 2R. Now 2R is equal to root 2A. R is equal to root 2A by 2. Make this as your equation A. Great. I'll say. Till now you got my point. Clear? Now, actually, our void is present here. Okay. So now we need to take the triangle ADC. So that only we can calculate the radius of our tetrahedral void. Got my point? What? Simply to? Exactly. But DCC in center, what happened? There will be another atom. But here, it's a void. Clear? Don't get confused. DCC, there we are having only body-centered cubic atom in the center. But here, it's void. Now, ADC, which is nothing but AD square is equal to AC square plus CD square. Okay. So, AD square is equal to AC square is 2A square plus CD square is A square. Where is P? Wait, I'll draw it. C, A, B, C, D, E, F, G, H. The variables can be, you can take it from anywhere. Okay, no issues for the variables. Now, AD square is equal to 3A square. Clear? AD is equal to root 3A. Till now you got this thing. Now, this AD has, see this AD I can show it in a diagrammatic form. A, your void, and your B. I'm not drawing the entire cubic structure. I'm taking A, D, and your tetrahedral void. Okay. So now R. And for void, we have to keep it as capital R. So here it will be 2R. Clear? 2 capital R plus 2 small r is equal to root 3A. 2 capital R plus small r is equal to root 3A. Capital R plus small r is equal to root 3 by 2 into A. Make it as B. Now divide B. Now B divided by A. Shall we make it? Shall I rub this thing? Okay, fine. Wait. After that, I have done it. Okay. Now divide. Shall I move to another slide? To have copied? Is it boring? No, na. Okay. Now I'm dividing. Okay. So B divided by A. R is equal to root 2 by 2A. Now A and A gets cancelled. 2 and 2 gets cancelled. So capital R plus small r is equal to root 3 divided by small r is equal to root 2. Correct? Yes or no? Now, capital R divided by small r plus small r divided by small r is equal to root 3 by root 2. Strike out the R and R, which means capital R by small r plus 1 is equal to root 3 by root 2. Now, capital R divided by small r is equal to root 3 by root 2 minus 1. Yes. Now, capital R by small r is equal to, what is the value of root 3? Minus 1.414 divided by 1.414. This is actually, I have brought this root 2 here. I brought this root 2 here. Okay. So now, calculate this thing and say the answer. And 0.312. You can't prove, but you are and follow this thing if you have any doubt. Okay. So now what's your answer? Money, have you done it or not? Money tricking la. Too bad. Actually, you have to subtract this thing and divide it by 1.414. What's your answer? You got it? Come on. 0.732. Sorry. 1. You can follow it or not? You got it? Super. 1.732 minus. Array, what's your problem? Multiplication subtraction doubt. Okay. 1.732 minus 1.414. What's your answer? 0.318. Wow. Now do this thing. 0. Divided by 1.414. 0.2248. So can we round it off as 0.225? So now capital R by small r is equal to 0.225. So capital R is equal to 0.225 R. This is your relationship between tetrahedral void and atom. Now you got my point. For octahedral void, what's your value? Here it's 0.225. Clear? Shall we move to next thing? Derivations. Each and every step is important. Okay. You can change the variables wherever it is. Have you written? Copy. Just go through this thing clearly. Okay. Slowly. After that, we can move to our next one. Derivation is here we can substitute, but still I have made it as complicated. Don't want to be complicated. I have shorted here. If you want, you can substitute and go for it. No issues. Okay. No substitute any variables. A, B, C can be anything, whatever it might be. But this method is the easiest. Clear? In your textbook also, I think this is the one which you have disclosed. Clear? Clear with this calculation? The end product you should be deriving for octahedral void, capital R is equal to 0.4 into small r. That capital R is your void, small r is your radius of atom. Okay. For tetrahedral void, 0.2. That should be complete. That's it. Okay. Clear? Now we shall go on to the next topic. You got, ma'am? Radius ratio and ionic ratio. What is radius ratio? Okay. Before that, I have a question. I have already taught you 4 solids. Ionic solid, covalent solid, metallic solid, molecular solid. Okay. Out of the 4 solids, okay, ionic solid is quite different because in ionic solid, the constituent particle will be of atom, that is ions, which is cation and anion. The rest of all the 3 solids, it is atoms. The constituent particle is atoms. Yes or no? Yes. So, in case of ionic solid, if an atom loses an electron, it will become cation. Yes. You're sure with this thing? Yes. If the anion gains the electron, atom gains an electron. At the end of the solid state, definitely I'll be becoming perplexed. Okay. Anion gains an electron, it will become an atom gains an electron, it will become an anion. Okay. So which one will be having larger size? Anion. Second, atom, cation, anion. Anion will be having larger size. Then atom, then cation. So the cation will be having least space. Okay. Now, coming to a point. Definitely, in covalent solid, metallic solid, and molecular solid, the particles, I mean the atoms will be arranged, the void will be seen. Okay. There will be a little bit of space, empty space will be there. That is point. In ionic solid, okay, the particles will be big. That is the anions. That will arrange. In the smaller void, the cation will go and see. We can't say completely there is no void. Of course, there will be void will be there. How comparatively, how closely you are packing, definitely there will be void will be present. No issues about the void. Void will be there. But I'm saying the packing efficiency. It will be more in terms of ionic solid because the cation will be very much small in size. When it is very much small in size, what happens here? It will go and sits in the voids. So the packing efficiency will be more in terms of ionic solid. Okay, only we are talking about the constituent particles. Now my question is, okay, so here, why we want to study the radius ratio and ionic ratio? What is the purpose to study? Huh? Radius ratio. Radius ratio in the sense, the cations and the anions radius. That is radius ratio. Great. Yeah, exactly. What is the purpose to study? Hydrogen is partial negative charge and chlorine is partial positive. Yeah, the hydrogen will be very small. See, that will attain polarity. Of course, that will be attain polarity. But what happens there, this is different, that is totally different. What happens in terms of ionic solid, they are ready to lose the electron. They are completely jump. But is the chlorine will release the hydrogen? No. Chlorine is highly electronegative. It won't release. In case of ionic, that's why I said the atom will lose the electron. Clear? Yes. Now, coming to the point, why you are studying the radius ratio in the sense, you are going to study this ionic solid. Okay. Only in ionic solid, you are going to study this radius ratio. That is radius of cation by radius of anion. Clear with this point? So far you got clear? Yes? Now, in states of matter, you have studied this thing. About studied it or not, I don't know, but it is there in states of matter. They will say about the connection between the two atoms. Okay, so here hydrogen is being very small. What happened? It is ready to go and bond. Okay, you know about electronegativity. Then only you know. So what happened? This chlorine, this is highly electronegative. This two bonds. So what happened? It be closely packed. So as a molecule, it's closely packed. The ions will not be getting separated. Clear. But Na and Cl, what happened? That Na will completely give the atom to the Cl, the ion to the Cl. Yes. So here, radius of cation, right? So far I'm repeating only this point. Now, it has three range values. Okay. The first radius range value is 0.2252. I'm saying why this ranges. Okay, first one is this is actually the smallest range value. This is the mid range value. This is the largest range value. You can take anything. If it is a cation or anion, see, if I'm taking, say for example, here, this 0.25 to 0.414 is the smallest value. Okay, so if you're just taking, imagine if your cation will be of this much size. This is 4.4142. 0.732. So your cation at the end you will come to know, you will come across what you're going to study. Okay, little bit large. Okay, and 0.732 to 0.99, it will be like this. Clear? This is the radius ratio. Okay, so if the cation is big, means that see this cation. Can't say in all the solids. Some rare cases, the cation may also be in large size. Okay, so it's just like interchange, interconvertible. Clear? So you can take anion also here, whatever it might be. If any one of the component, cation or anion, if any one of the component is large, means definitely the other will be small. Definitely the smaller will go and occupy the voids. Come on, any doubt? No. Okay. So what happens here? Remember, the first one, the range is 0.224. So if it is this much small in the sense, definitely the 4 anions will come and surround here. I want to be a little bit defined. Okay. This is right. Okay. So the 4 anions will come and surround this cation because it's being very small. Now the size is getting little bit bigger. So what happens? Are you not feeling well? So here, coming to the second range, the size is little bit larger. It is in a mid range. So what happens here? 6 atoms can come and sit here. 6 anions. Okay, that is like FCC. Face points: top, bottom, left, right, front, back. Okay. Now, in case of radius ratio, third range, this range, you can see your cation will be this much big. So all your anions will surround like this. Can you spot the difference? Okay, it will be 8. It will be actually closely packed. Okay. Can you note the difference? No, don't come to end center and face center. Wait, don't confuse that thing with this thing. Wait, I'll make it clear. Wait, this is the cation which is having a very small range. Clear? This is the anion. Don't compare the ends. Why are you comparing the end center here? Don't see this diagram and imagine all these kinds of things. Okay, I'll conclude and then you can ask your doubt. Okay, so here what I have said is it's little bit big. So what happens? The accountation of anions will be more. So what happens is anions will be here. So here it is a big cation. So all the 8 anions can surround it. Depends upon the range value. So void. What is here? 6. It's a octahedral void. So for this stage, definitely your cation will be very small. 4 anions will be surrounded by it, and the void will be what is man? Tetrahedral. What will be the coordination number? Central particle surrounded by how many? 4. Make the point out of it. Okay. So the void for this, it will be having octahedral void, and the coordination number will be 4. Okay. And your radius tetrahedral void, and the coordination number is 4, and your range is of this thing. See, it can be either this cation, it's very small. Now, you're going a little bit further. So what happens? This cation is surrounded by 6 anions. So what will be the void here? It's octahedral void, and your coordination number is 6. See here, I know you people will say the coordination number is 8. But what is a void here? Ha ha ha. Shall I rub this diagram? What is a void? Huh? Void is so small. Look at C. The anion. I'm technically the weakest person. Huh? Here. Where is undo? Top left here. That square box. See, I'll draw. Don't worry. The anions are surrounded like this, right? So this anions will be in the lattice points. This is small. So your void is big. Can you imagine? Your void is big. This void is known as cubic void. This is cubic void. Okay. So make sure, note the range and write the tetrahedral void coordination number, and here octahedral void coordination number, cubic void and coordination number. Okay. So for the example for this is zinc sulfide, and I'll draw the picture for everything. Okay. NaCl, and here it is CCl. Okay. This is the radius ratio range. Clear? If this is in this range, it will be tetrahedral void. See, now, what is the example of? Cesium chloride. I'll draw everything. In the forthcoming slides, everything will be coming. Okay. Now you got this point C. 1 minute. Wait, see, read this question. A bromine ion size 195, calculate the radius of the cation, just fits in the tetrahedral void. So tetrahedral void means definitely just fit means you have to take out the minimum value. So you have to know this. Clear? Very, very important. This thing, void coordination number. Okay, examples in your text, they have disclosed more examples, you can go for it. Clear with this thing? Now. What are all the chapters for your first term? Solid state, then? What chapter? So next chapter, where shall we go for haloalkenes and haloarenes? I seriously, huh? That's okay, man. 1, 2, 3, 4, 5, 6, 7. Okay. See, actually, this cubic void is there will be 8 lattice points. Okay, it is in SCC. In simple cubic cell, what happened? In SCC, what happened? The big void will be there. That big void will be shared by all the lattice points. I'm saying about voids. Don't think there is one big atom is present. This is not BCC. SCC, there will be a big void, that is cubic void. This is a simple cell. Wait, I'll draw a diagram for your imagination. See, this is all your lattice points. Simple cubic cell, right? And your cubic void will be of like this. Will be big. So what happens? This cation will be big, and all the anions present in the lattice points will be small. That is what I have represented. Okay, solid state is imagined. Clear? For triangular void, see, just take a note of this. Okay, this is a range. Like for octahedral void, tetrahedral void, cubic void. This is for triangular void, the range. For in any questions they'll ask. Just they have been only disclosed this thing in your NCR. You don't want any kind of calculations. This one is the octahedral, tetrahedral, cubic void. Their ranges. Now this is triangular void range. For the problematic thing, just want to move. Clear? Shall we move to our next thing? Shall we calculate the problems? Yes? Then what are all the things is left out? Do this problem. What is given? What is the information given? Bromine ion has size 190. So the anion's radius is given 195 picometer. Clear? Calculate the radius of the cation. Just fits into the tetrahedral voids. So you know the radius ratio of tetrahedral void is 0.225 is equal to radius of cation divided by radius of anion. You know the radius of anion 195. You don't know the radius of cation. Just multiplication. Here, yeah. Actually, that's 0.225 in terms of radius. That is a radius ratio. Okay, that is a radius ratio. And make it in forms of picometer itself, you do and say. I'll do it here. Wait, I'll do it. So the value of this thing is 438. Sure up. See, substitute 195 here. Make it as picometer itself, no problem. There is no options disclosed. Wait now. 0. I don't believe you. I'll do it on myself by the help of calculator. 195. 43.87. Okay, picometer. That's okay. This is the radius of cation. Read the second question. What's the second question? What they have been conjured. So check whether it's like octahedral void or not. See, if the radius is 82 picometer. This is the radius of cation. We already know the radius of anion. So just divide it. Okay, so you will be getting obtaining one value. Just see the range, whether it comes under octahedral void or not.
Okay. The first step you like this fits into the right.
Just fits means minimum value is enough, right?
But in another perspective, you see like if above that range, it doesn't fit. It doesn't
Above
fit.
range, it doesn't fit down, which means
It means like if 3 meters, the void is 3 meters. It just fit. Then if we go for 4, it doesn't fit in the doesn't come under
no,
the
the particles can also be no. It can be that kind of things. No issues. See, the void is like you are having 5 centimeters. Okay. Smallest particle is 1
be some space. You can get. Sometimes the space will not be there. That's why in first class I said about the sponge. Sponge is a solid. Solid compressed. Okay, so what happens is the particles can be compressed, but again it's remaining in shape form. So you can't predict which is what is the range? 0.442, which means 0.414 to 0.734. It comes under octahedral void. Very good. Shall we move to our next thing? Do you want me to calculate this thing? Second one? No. Do this thing. Easy peasy question. You shouldn't do it in that way. I have given the radius of cation and anion. You have to check with that range. I have done a greatest mistake by giving NaCl. Just divide the cation by anion and find the range. See, I have given for NaCl. Suppose if there is another compound there means what you will do at that time? You have to calculate the radius of cation by radius of anion. How smart are you are? Seriously. 2K kids are really, really clever. Huh? Our generations, if ma'am says to draw anything, means we will draw. From the A to Z, we will draw. Huh? So 95 divided by 181. It is 0.524, which means it comes under the range of 0.414 to 0.73. So it is under octahedral void, coordination number 6. You have to only find out by this way. Okay. Shall we move on next topic? Maybe. Oh, exactly. You're my boy, seriously. What happened, man? How fastly you're saying this? I'm just, oh my god, how this guy is know this? Huh? Okay, fine. Now, types of crystal structure. Okay. You are having NaCl, you are having cesium chloride, you are having zinc sulfide, you are having magnesium chloride, having graphite, and everywhere the crystalline structure is different. Clear? Definitely it's different by its bond angle, by its edge length. But the crystal arrangement, that is different. Okay. So in that crystal structure, there is actually, in up to your NCERT syllabus, it's AB type, AB2 type, AB2O4 type, and mixed oxides. Have you heard anywhere about mixed oxides? It's a composition of two oxides. Okay, I'll teach you. These are the 4 major types. First, AB type. In AB type, there is 3 types. Okay. It is. Have anyone seen Radheshyam? No. No. Okay. Apart from all that kind of cinematic and filmy things, have you seen? No one. Huh? No, I'm trying to say that is related to this chapter, man. I'm trying to connect. Okay. So in that, like in the climax scene, what happened? The astrologer, he will say, no matter in this world is 100% accurate. Likewise, people say the crystal structure is arranged in a regular 3-dimensional structure, but still it's imperfect. How is this? That you will be seeing in your deficiency, that is imperfections in solids. So if you get a chance, look at it. Okay. In AB type, there is 3. First one is NaCl type. Okay. Second one is ZNS. Third one is CCl type. Fine, anywhere. Second one is cesium chloride. Third one is Z. Okay. Now, this NaCl type, all the chlorine ions, actually they have been detected by the kind of, the microscope. You guys want any break? Okay. Huh? Who said I will be leaving you at 6:30? What I said yesterday? Any? Okay, I'll leave you at 6:30.
Oh my God, how loyal you are. Seriously. Okay. So all these chlorine ions will go and sit, have the arrangement of CCP lattice. See, this thing, everything is experimental questions. Okay. So this sodium ion will go and sits in the edge and one at the body. So now shall we draw the structure? Okay. See, for CCP is nothing but your FCC. Okay. So Cl minus, Cl minus, Cl minus, Cl minus. You guys can also draw. Okay, this is the CCP, correct? Now, the Na plus ions, it will be sitting in the edges. Na plus, Na plus, 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 plus. Right, I have marked the Na plus in all the 12 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. Now, one Na plus will be occupied in the central body center as a void. Okay, so this Na plus. Because in Na structure also there will be little bit of voids will be there. Okay, no solids is perfect. There will be little bit voids will be there. Okay, so now calculate. So the Cl minus ions is present in FCC. So for corner 8 into 1 by 8 and for FCC 6 into 1 by 2. Am I right or wrong? This is for chlorine ions. Right or wrong? 1 plus 3 is equal to 4. And now for your Na plus ions, it will be like in the edges it is 12 into 1 by 4 plus it is 1 in the body centered as a void. So totally this is also 3 plus 1, 4. So how you can write this? Na to Na4, Cl4. Make it in a simple ratio. It is 4, 4 gets cancelled as 1, 1 and your NaCl solid will be obtained. This kind of arrangement is AB type. All the things is AB type. This kind of arrangement is there in your salt, what you're eating. So daily when you're eating, remember the arrangement. Okay. When you're having a scoop or spoonful of rice, or when you're taking in your hand, remember there is this kind of arrangement is there. All the chlorine ions are located at the CCP lattice and the Na plus ions are present in the edges as well as one as a void in center. Now, what type of void? Exactly, octahedral void. Very good, octahedral void. Because if you just take one, I mean like anion or cation, it is surrounded by 6. So, correct. So what is the void? It is octahedral void. The coordination number will be. You're all sleepy. No? Then your voice should be like 6. Yes? Clear? Clear with this type? Now shall we move for the next one? See. Can I go? Front. So these are all the other examples which will be similar to this NaCl. Okay. LiCl, NaCl, KBr, RTI, silver chloride, silver chromate, everything comes under this AB. See, in this AB there is 3 types. This NaCl type, this all things will be coming. Next one is this thing. 6:38. I'll leave you at 6:30. It's only 6:26. Wait, I'll leave you at 6:30. You'll be having an extra class. not today. Somehow to complete a solid state. Got it? Shall we move for another type? With another type, I'll complete. Don't worry. Ah, no, ma'am. Only your, your mouth says no, ma'am. See, he is saying, I want to call me. No issues. Copied. Everyone, shall we move to next one? Cesium chloride. In cesium chloride, what happens means, see, all the cesium, the chlorine ions will go and sit in the lattice points as simple cubic cell. That is, in 8 corners, the 8 Cl ions will be present. Clear? And the one, that is the Cs plus, that is the cesium cation, will be located as a big void, as a cubic void in between the SEC. This kind of arrangement is seen by a microscope. Clear? Okay, see, it will be like this. This is not body. One cesium ion, that is cation, as a void. Body is different. This is SEC. This is SEC. Simple cubic. Okay. This is right. And the one cesium cation will be occupied this cubic void. So what kind of void is present in cesium chloride? Cubic void. What is the coordination number? 8. And now shall we calculate cubic void? The ZF. So the Cl ions will be having 8 into 1 by 8. So which will be having 1. And the cesium cation will be having 1 by 1 at the center. So as such, the simple ratio will be CS1, Cl1. This is cesium chloride. So what are all the rest of the examples? I've taken. Faster. முடிச்சிட்டு question paper generate பண்ணலாம். Should be fine. Okay. So these are all the rest of the examples. Cesium chloride, already discussed. Cesium bromide, cesium iodide. Only the cesium families will come here. It will become under the cubic void. Clear? Third one is ZnS type. Okay, I'll give an intro and I'll make it in my next class. Okay, I'll have an 629. Okay, then I'll do it. This is ZnS. That is Zn2 plus and S2 minus. You know about the oxidation state charges, right? I don't want to say, right? This S2 minus will be located as a CCP lattice. That is as FCC. This will be as CC. And this zinc 2 plus, no. Actually, what happened? It will be occupying the alternative tetrahedral voids. It's all from the experimentation. If you are asking how means, the arrangement itself is like that. Okay. So, cations occupy the corners. Of course, it can be, but in the rarest case. Because, if there is like, if all the anions will be bigger. Of course, the cation sometimes will be bigger. Always the cation will be go in the mid because it is in the void. It will go and sit. The probability will be more for the cation to go and occupy. Clear? Right? With the FCC. Yes. Now, see, here we can draw 4 body diagonal, right? So these are all front, back. Another one will be front, back, and front. Out of this, we will be obtaining 8 tetrahedral voids. But there is only alternative tetrahedral void. There the zinc cation will go and sit. Clear? So it will be like 1 here, 1 here, 1 here, and another one. Got it or not? Now, this we can calculate the Zutta, okay? The radius ratio that will be for SC2, it is occupying all the corners 8 into 1 by 8 plus the faces 6 into 1 by 2, which is 4. And the zinc 2 plus is occupying the 4 alternative tetrahedral voids. So the radius is Z10 S4. So on simple ratio, Z10 S3 obtained. Clear? So void will be tetrahedral void. Coordination number will be clear. So the rest of the examples. Now this is little bit easy. The next one is we are getting into it. AB2 type. You want me to complete here, or you want me to take for another half an hour, or you want to take? No. I'm not seeing you, man. I'm just asking in general. You just don't think that I'm just only indicating you. No. What's your opinion? Huh? Today free only. It's Friday. Oh, day, jolly day. Huh? Okay. Huh? Okay, the class is getting dispersed, but wait, I'll give you a simple revision and then you guys can. Because I'm to having work, that's why. Okay. See, after that we are going to see AB2 type and AB2O4 and mixed oxides. That will be 5 minutes. And next we are getting into Bragg's equation. Have you heard anywhere Bragg's equation? Okay. So Bragg's equation and imperfection solids, that's it. Solid state completed. Electrical properties and magnetic properties. That's only for the solid. Whether if I'm taking this mobile phone, it is having the conductive nature or not. That's the electrical properties. How far it is reacting to the magnet, that's a magnetic property. Okay. So that's how probably the next class 1 hour it will be getting over. And we can solve problems. Okay. Definitely 1 hour, if you're just like, you need to, delegate 1 hour for solving problems. After that, definitely you guys will be done. So till now, do you guys have any doubt? Clear? Clear? Go through your NCRT. Okay. So actually, there'll be more examples will be there in NCRT. Okay. Go and study all the concept is same. Concept is what I have said. The concept is same. But you can go for more examples in your NCRT. Okay? Yes. Thank you so much. We can see in our next week, Thursday class, I'll try to complete solid state and then we can go for organic chemistry. Okay? I'm so happy in teaching organic chemistry. Seriously. Everyone is happy. Okay. Guys, if you're feeling any difficulty in my teaching, please let me know. Yeah. Super. Thank you. Yeah, I have already disclosed my number. If you don't feel low at any time, definitely we will be struggling. If you have any doubt, you can WhatsApp me or can call me. You can ask the doubt only for doubt. Okay. Number I have given. No. And I get any other. I'll say. Okay. My next class I'll say. Thank you. Enjoy your weekends. Okay. Enjoy. Ama. Yes.
Thank you, ma'am.
Thank you. Thank you. Thank you.